On the 7th day of December 1941, Pearl Harbor was engulfed in flames, and within 72 hours, the United States military found itself grappling with a colossal logistical crisis, one that had absolutely no connection to naval vessels or aerial combat. Across the vast expanse of the Pacific Theater, from the distant Philippines to the isolated Wake Island, American forces were forced to endure their existence in canvas tents that, under the relentless tropical downpours, would simply disintegrate within a mere 3 weeks. The morning military briefings in the War Department became increasingly somber as field reports began to detail entire supply depots submerged in water, vital ammunition rendered useless, and soldiers hospitalized with pneumonia due to their temporary shelters literally collapsing during the monsoon season. The construction of traditional wooden barracks required highly skilled carpenters, weeks of dedicated construction time, and a supply of lumber that was simply unavailable on remote coral atolls. The Navy's calculations projected that 18 months would be needed to erect conventional housing for the substantial forces they needed to deploy immediately. In Washington, D.C., Brigadier General Eugene Raybould stood before a crisis table, meticulously covered with weather charts and detailed construction timelines. His team of engineers presented him with an equation that seemed utterly impossible to solve. They urgently needed structures that could be manufactured in Pennsylvania, transported over 10,000 miles through waters infested with submarines, assembled by exhausted Marines who had never previously handled a wrench, and crucially, withstand every extreme the Pacific Ocean could unleash upon them. This included scorching 130-degree heat, Category 5 typhoons, monsoons that dumped 15 inches of rain in just 6 hours, and the very real threat of impending Japanese bombing raids. The standard Army tent, costing a mere $12, offered protection for only 1 month under the harsh jungle conditions. A wooden barracks building, on the other hand, came with a price tag of $8,000 and necessitated a dedicated construction crew for 6 weeks. Neither of these options was viable when island hopping across the Pacific and requiring immediate shelter for 50,000 men. The British, having engaged in conflict for a longer period, possessed valuable experience gained in North Africa, which offered a potential solution. Since 1916, they had been utilizing Nissen huts, a semicircular steel shelter originally conceived by Canadian engineer Peter Nissen during the First World War. These corrugated iron half-cylinders were designed to house 30 soldiers, required no specialized labor for assembly, and proved remarkably resilient against sandstorms. However, the Nissen design presented several critical drawbacks for deployment in the Pacific. The British iteration employed heavy steel panels that necessitated specialized lifting equipment. Furthermore, its ventilation system, adequate for the Libyan desert, transformed the interior into an unbearable steam cooker within the oppressive humidity of the Philippines. Most critically, each hut required custom foundation work, involving either pouring concrete or constructing wooden platforms, which inexorably led back to the very problem of needing skilled carpenters. Raybould's team calculated that shelter was needed for an astonishing 2 million personnel spread across hundreds of islands and bases. The sheer scale of the undertaking was brutal. At conventional construction rates, the war would have concluded long before half of the deployed troops had even secured adequate roofing over their heads. Soldiers were already penning letters home, describing the disheartening reality of waking to find their boots filled with rainwater, the overnight growth of persistent fungus on their uniforms, and the terrifying experience of their temporary tents collapsing during storms, forcing them to scramble through the mud at 3 in the morning. The Medical Corps reported that respiratory infections were incapacitating more men than enemy action in certain operational sectors. This was not merely a matter of comfort, it was an imperative for maintaining a fighting force that would not succumb to the elements before ever engaging the enemy. A widespread call was issued to American engineering firms, university research departments, and the Navy's own construction battalions. The specifications sounded as if they were drawn from the pages of science fiction. Design a building that weighed less than a jeep, could be transported on a single rail car, required no foundation whatsoever, could be assembled in a single day using only basic tools, cost less than $1,000, and could withstand conditions that routinely destroyed permanent structures. And, as if that were not enough, 10,000 such units were to be ready for shipment within 6 months. It was February 1942, and somewhere in Rhode Island, a team of engineers was on the verge of transforming architectural impossibility into tangible reality. The blueprints for the Nissen Hut arrived at the Navy's Bureau of Yards and Docks, a peculiar outcome of wartime cooperation. British engineers, immensely grateful for American supply shipments, generously shared detailed technical drawings of their First World War shelter design. These depicted 16-foot-wide semicircular tunnels constructed from corrugated iron sheets bolted to a wooden frame. Commander John Philip Drosfeld meticulously studied the specifications, immediately recognizing both the ingenuity and the inherent problems. The genius lay in the arch shape, which naturally deflected wind and shed water without requiring complex engineering. The problems, however, presented a formidable list that would undoubtedly doom the design in the challenging conditions of the Pacific. The British huts weighed 3 tons when disassembled, necessitated foundation bolts drilled into concrete, and utilized an internal wooden frame that served as an irresistible buffet for termites in tropical climates. Drosfeld encircled the ventilation specifications in red ink, noting that the 2 small windows, perfectly adequate for Scottish weather, would transform these structures into ovens in Guadalcanal's sweltering 98-degree average temperature. However, another American voice was entering this critical conversation, emerging from an unexpected quarter. Buckminster Fuller had been an ardent advocate for prefabricated housing since the 1920s, although most architects dismissed him as an eccentric. His concept for the Dymaxion house, factory-built, lightweight, and assembled on site, read like a prescient prophecy. In 1942, Fuller's radical ideas about mass-producing housing in a manner akin to automobiles, utilizing industrial materials instead of traditional lumber, and prioritizing rapid deployment, suddenly seemed far less outlandish when the nation urgently needed to construct an entire city's worth of shelter every single month. While the military had not directly consulted Fuller, his published papers circulated extensively throughout engineering departments, and his central insight proved to be of invaluable importance. Treat buildings not as construction projects, but as manufactured products. The Navy consolidated this revolutionary thinking at their facility located at Quonset Point, Rhode Island, a newly commissioned air station situated on Narragansett Bay. The choice of location was not arbitrary. Rhode Island possessed a rich heritage of deep manufacturing expertise in sheet metal, stemming from its prominent jewelry and silverware industries. Furthermore, it offered proximity to crucial steel mills in Pennsylvania and shipyards well-versed in the requirements of marine-grade corrosion resistance. In March of 1942, the Navy assembled an extraordinary team. Structural engineers from the Strand Steel Corporation, who had prior experience in constructing prefabricated farm buildings, architects from the George A. Fuller Construction Company, specialists in rapid assembly methods, and Navy officers who had actually served in the Pacific and possessed an authentic understanding of what typhoon-proof truly meant, beyond mere theoretical specifications. The team leader, Otto Brandenberger, brought with him farm building experience that proved to be precisely what was needed for this monumental challenge. His strand steel barns utilized self-supporting arched panels, obviating the necessity for an internal frame. This meant no wood for termites to consume and no complex joinery that could fail during violent storms. Brandenberger's audacious proposal was to completely eliminate the Nissen Hut's wooden skeleton, allowing the corrugated steel skin to bear all the structural loads. This radical concept defied conventional architectural wisdom of 1942, where steel was predominantly reserved for bridges and skyscrapers, not for standalone self-supporting structures. However, Brandenberger was confident, having witnessed his barns withstand Midwestern tornadoes without internal framing, and he was willing to wager that the same principle could be successfully scaled up. The British contributed another indispensable element through their hard-won and painful experiences. Their Nissen huts in Burma and Singapore had provided them with a stark, practical understanding of how tropical environments systematically destroy buildings. Fungus, they learned, was not merely cosmetic, it literally consumed wood preservatives and paint within a matter of months. Humidity did not simply make things damp, it relentlessly corroded metal fasteners until entire roofs collapsed. Insects were not merely an annoyance. Carpenter ants could reduce wooden support beams to hollowed-out shells within a single season. The British reports read like harrowing accounts of disaster, but they furnished the Quonset team with an exhaustive checklist of every single factor that had to be engineered out of the design from its very inception. There was to be no wood in contact with the ground. All steel components were to be hot-dip galvanized, not merely painted. Ventilation had to be sufficiently robust to actively prevent condensation. Every fastener was to be designed for easy access and replacement without the need to disassemble the entire structure. By April of 1942, a hybrid vision began to materialize. The plan was to incorporate the brilliant arch geometry of the Nissen Hut, meticulously strip away every element that contributed unnecessary weight or vulnerability, integrate Fuller's philosophy of mass production, harness the immense power of American steel manufacturing, and engineer every single detail to withstand the specific hellish conditions of Pacific Island warfare. On April 15, 1942, Otto Brandenberger entered a Quonset Point warehouse accompanied by 30 engineers and facing a deadline that would have been considered laughably impossible if the war situation had not been so dire. They had 60 days to design, build a prototype, rigorously test, and obtain approval for an entirely new building system that, at that moment, simply did not exist. The team operated in continuous shifts, working around the clock, snatching sleep on cots pushed against the warehouse walls, subsisting on potent Navy mess hall coffee and the sheer pressure that either forged brilliance or led to complete breakdown. Brandenberger strategically divided his crew into specialized units. One group focused on aerodynamics and structural load calculations. Another was tasked with devising a method for nesting components efficiently for shipping. A third unit dedicated its entire efforts to resolving the complex joint and fastener challenges that had plagued the British design. The first truly radical decision was made on the third day. Traditional architectural drawings typically required weeks to produce, a luxury the team simply did not possess. Instead, they embraced a real-time building process. A detail would be sketched in the morning, fabricated by the metalworking shop by the afternoon, subjected to overnight testing, and revised by dawn. This iterative prototyping approach, commonplace in 2025, was revolutionary in 1942, when buildings were customarily designed entirely on paper before a single piece of material was cut. The vast warehouse floor rapidly transformed into a sprawling laboratory, littered with the remnants of failed joint experiments, bent test panels, and increasingly refined versions of each individual component. The engineers adopted a technique borrowed from aircraft manufacturing. Every single part was assigned a unique number. Every revision was meticulously documented, and absolutely nothing proceeded to the next prototype generation without thoroughly addressing and solving the failure points identified in the preceding version. The dimensions were dictated by brutal practicality rather than aesthetic preference. The width was fixed at 16 feet, the maximum that could fit on a standard railcar without requiring special permits. Each section measured 20 feet in length, short enough that 4 men could comfortably lift a panel, yet sufficiently long to create usable interior space. The final assembled length of 48 feet provided housing capacity for 36 men with bunks, or the flexibility to be converted into office space, medical stations, or vital supply storage. The Quonset team discovered that this specific size represented an optimal balance point in structural engineering. Making the structure smaller would have resulted in wasted shipping capacity. Conversely, increasing their size would have rendered the panels too heavy for efficient field assembly, or the arch itself would have necessitated internal supports, thereby reintroducing all the problems they were striving to eliminate. The calculation of the arch's radius consumed 2 full weeks of the 60-day deadline. A radius that was too flat risked the wind forces peeling the structure open like a sardine can. A radius that was too steep would have resulted in wasted interior headroom and complicated end wall geometry. Brandenberger's team ultimately settled on an 8-foot radius, forming a perfect semicircle that provided 7 feet of headroom at the sides and created what structural engineers term a self-bracing arch. The corrugated steel, by its very nature, naturally assumed and maintained this curve, allowing for thinner and lighter panels compared to what would have been required for flat sheets to achieve equivalent strength. They conducted load calculations indicating that this design could theoretically withstand snow loads of up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. However, theoretical calculations and the actual fury of Pacific typhoons were vastly different adversaries. By the 40th day, they had produced something that showed promise. A veritable Frankenstein's monster of riveted panels, experimental joints, and repurposed hardware. The first complete prototype was erected on May 25, 1942. 6 sailors, having received only 4 hours of instruction and equipped with basic hand tools, successfully assembled it. The assembly time, 14 hours, was encouraging but still fell short of the Navy's requirement for single-day construction capability, as marine landing schedules could not accommodate multi-day building projects. The team immediately identified the primary bottleneck, the flooring system. They had initially attempted to incorporate a wooden floor as an integral part of the package, but it proved to be the slowest element to assemble, and, furthermore, the first component to succumb to rot in tropical conditions. The solution arrived with an elegant simplicity. Eliminate the floor entirely from the basic design. The hut would now rest directly on whatever surface was available, be it coral, sand, dirt, or, if exceptionally fortunate, gravel. For applications requiring finished floors, these could be added later as a separate undertaking. However, the fundamental shelter achieved its weather protection objectives without them. This singular decision drastically reduced assembly time to a mere 8 hours and achieved a weight reduction of 1,200 pounds per unit. On June 10, 1942, the final prototype stood complete. It comprised 96 corrugated steel panels, each weighing less than 50 pounds, which bolted together to form 720 square feet of enclosed space. The total material cost amounted to $1,394, with a total weight of 9,000 pounds. The true test commenced when the Quonset prototype faced what could only be described as the engineering equivalent of an intense interrogation. Navy structural engineers arrived equipped with wind load tables, typhoon data meticulously gathered from meteorological stations across the Pacific, and a healthy dose of skepticism regarding whether this humble, corrugated tunnel could truly withstand the relentless onslaught of nature on tropical islands. The figures they were working with were not theoretical. They were derived from actual devastating weather events. Typhoon Gloria, which battered Guam in November of 1940, registered sustained winds of 140 miles per hour, with gusts reaching 180. The devastating 1935 Labor Day hurricane, which tragically claimed 400 lives in the Florida Keys, produced winds so ferocious that they stripped paint from buildings and drove wooden planks through palm trees with the force of spears. If the Quonset huts failed during a storm, the consequences would extend far beyond mere property damage. They would result in the loss of servicemen's lives and the destruction of critical equipment. Brandenburger's team initiated their evaluation by examining the fundamental physics behind why the arch shape was so effective. When wind encounters a flat wall, it generates what engineers refer to as a pressure coefficient. The wind exerts direct force against the surface at its maximum intensity. In contrast, a curved surface skillfully deflects the wind upward and around the structure, significantly diminishing that pressure. One could visualize this by comparing how water flows smoothly around a river stone versus how it violently slams against a dam wall. The semicircular profile of the Quonset hut meant that hurricane-force winds would flow over the structure rather than attempting to breach it. The corrugations introduced a second layer of ingenious design. These ridges, running lengthwise along the panels, imparted structural rigidity in a manner analogous to how folding a piece of paper makes it substantially stronger than leaving it flat. Each corrugation functioned like a miniature I-beam, effectively resisting bending forces that would easily crumple smooth sheet metal. The mathematical analysis became particularly fascinating when examining how loads distributed themselves throughout the arch. In a conventional rectangular building, the roof exerts downward force on the walls. The walls transmit this force to the foundations, and the entire structure relies on these vertical load paths remaining intact. Storm winds could literally lift roofs off because their separate components were merely resting atop the walls. The Quonset arch fundamentally altered this dynamic. It formed a single, continuous curve where every panel seamlessly shared the load with its adjacent neighbors. Engineers termed this a compression ring, and it operates on the same principle that allows ancient stone bridges to stand for centuries without the need for mortar. The hoop stress, representing the tension attempting to spread the arch apart at its base, was effectively resolved by the ground itself. Each Quonset panel was secured to its neighbor with 3/4-inch steel bolts spaced every 6 inches, thereby creating what was essentially a 48-foot-long steel cable meticulously wrapped in an arch configuration. However, theoretical strength held no value without rigorous testing. Consequently, the Navy devised validation experiments that bordered on the masochistic. They constructed a full-scale Quonset hut at Davisville, Rhode Island, and outfitted it with an array of strain gauges, pressure sensors, and deflection meters. Then, they patiently awaited the arrival of the first major nor'easter. On March 3, 1943, a storm descended with 75-mile-per-hour winds and substantial snow loading, the perfect conditions for a test. The instruments recorded the structure flexing by less than 2 inches at its apex, returning precisely to its original shape once the wind subsided. The panel joints remained secure. Not a single drip of water entered the interior. The structure performed exactly as the calculations had predicted, a fact that was both exhilarating and profoundly unsettling, as it meant they were about to entrust the lives of thousands to this design. The testing within the tropical environment proved to be a more formidable challenge than evaluating wind loads. It was impossible to accurately simulate years of jungle conditions within a Rhode Island warehouse. Therefore, the Navy transported a test unit to the Panama Canal Zone, an area characterized by an average humidity of 85% year-round and temperatures consistently above 80 degrees Fahrenheit. 6 months later, the comprehensive report was submitted. It indicated minimal corrosion on the galvanized panels and no observable structural degradation. However, significant issues arose concerning internal condensation. When the hot, humid air came into contact with the relatively cooler steel surfaces at night, water literally precipitated from the ceiling inside the hut. The solution required the addition of ventilation louvers at both ends of the structure, as well as along the ridgeline. These strategically placed openings allowed hot air to escape and facilitated airflow without compromising structural integrity or weather protection. While these vents added $47 to the unit cost, they transformed the hut from an unbearable steel sauna into a space that humans could genuinely inhabit in the oppressive tropical heat. The final engineering hurdle revolved around the foundation. How could a 9,000-pound building be securely anchored to loose sand or coral without the necessity of pouring concrete? The answer emerged from the principles of tent technology, scaled up. Robust steel stakes driven firmly into the ground connected to the hut's base via adjustable tension cables. For harder surfaces, the team devised a bolt pattern that permitted the hut to be mounted directly onto wooden sleepers or pierced steel planking. The inherent beauty of this anchoring system lay in its adaptability. The structure could subtly flex in response to ground movement without experiencing structural failure or tearing itself apart. In June of 1942, the War Production Board officially approved the manufacturing of the Quonset Hut. What followed was a remarkable demonstration of American industrial capacity operating at its absolute zenith. The Navy awarded contracts to 10 major steel fabricators situated across the Midwest and Northeast. Companies that, mere months prior, had been producing grain silos and water tanks, but were now rapidly retooling for the production of vital military shelter. The Strand Steel Corporation converted its entire Penrose facility, located just outside Philadelphia, to exclusively manufacture Quonset huts. The George A. Fuller Construction Company took over a former automobile parts plant in Chicago. Great Lakes Steel dedicated 2 of its rolling mills solely to the production of corrugated paneling. By August, these factories were collectively churning out an astonishing 1,500 complete huts per week, and this production rate continued to climb. The manufacturing process drew heavily upon the efficiency principles of automotive assembly lines. Massive steel coils, each measuring 4 feet wide and containing enough steel for 30 panels, arrived via rail. Specialized rolling machines then corrugated the flat steel, imparting those essential structural ridges at precisely 2 and 67/67-inch intervals. This corrugating process also had the effect of work-hardening the steel, rendering it significantly stronger than the original flat sheet. Following this, the panels entered galvanizing tanks, where they were immersed in molten zinc heated to 850 degrees Fahrenheit. This zinc coating was not merely paint. It represented a metallurgical bond that would sacrificially corrode, protecting the underlying steel from rust. In the corrosive saltwater air of the Pacific, this galvanization process proved to be the critical difference between a lifespan of 5 years and one of 50 years. Although this treatment added an additional $112 to the cost per hut, it became a non-negotiable requirement after field reports indicated that ungalvanized steel was corroding through completely in as little as 8 months. Each complete hut kit was meticulously packaged with an obsessive focus on shipping logistics. The 96 corrugated steel panels were designed to nest inside each other like stacked bowls, dramatically reducing the package height from 8 feet to a mere 14 inches. The end walls, constructed from plywood sheets with pre-cut door and window openings, were packed flat between the steel panels. All fasteners, bolts, and hardware were consolidated into a single wooden crate, which also contained clearly illustrated assembly instructions specifically designed for individuals who might not possess fluency in English. The entire kit was efficiently loaded onto a single standard 40-foot-long flatbed railcar. This remarkable packaging density was paramount, as every train destined for West Coast ports was carrying either Quonset huts, essential ammunition, vital food supplies, or critical vehicles. There was absolutely no room for inefficient cargo. The complex choreography of shipping became an operation of remarkable scale and precision. Trains depart Philadelphia and Chicago every day, bound for San Francisco, San Diego, and Seattle. There, at the docks, await Liberty ships and vessels designed for specialized freight. Longshoremen, using crane systems originally engineered for tanks and artillery, efficiently load entire habitation units into the holds. One Liberty ship alone possesses the capacity to transport 200 Quonset huts, along with their necessary fastening hardware, providing accommodation for 7,200 individuals. The War Shipping Administration meticulously oversees every cargo manifest, recognizing that these structures are not merely buildings but vital strategic assets. A hut dispatched to Guadalcanal in September could, by October, house a bomber crew, determining the critical difference between operational aircraft and pilots forced to endure the elements in the mud. The true brilliance of the Quonset design truly manifests during the assembly process at the destination. The Navy's construction battalions, famously known as the Seabees, devise standardized methods that transform the erection of shelters into a meticulously coordinated operation. A team of 6 individuals can assemble one complete hut ready for occupancy within 8 hours. The procedure commences with site preparation, leveling the ground, clearing any vegetation, and, if feasible, laying down a gravel base. 2 individuals manage the end walls, while the remaining 4 work with the steel panels. These panels exhibit a 6-inch overlap and are secured together using 3/4-inch fasteners. This assembly requires no welding, no concrete, and no specialized trades. Only wrenches, a level, and individuals capable of following illustrated directions are needed. The speed record for assembly was established on Espiritu Santo in January of 1943, when a specially trained CB crew erected a complete hut in a remarkable 4 hours and 17 minutes. However, this was largely for show. The genuine achievement lies in the sustained production across hundreds of islands, where crews erect 5 or 6 huts daily, week after week, thereby constructing entire bases at a pace that outstrips the Japanese ability to destroy them. By December of 1943, monthly production reached 8,000 units. The logistical network operated with such efficiency that huts ordered in Pennsylvania arrived in New Guinea within 40 days, inclusive of sea transit and trans-Pacific transportation. The cost analysis further illuminates the success. Each Quonset hut offers weatherproof accommodation for 36 men, costing $1,394 in materials and requiring approximately 60 man-hours for assembly. This stands in stark contrast to conventional barracks, which necessitate $12,000 in materials, 400 man-hours of skilled carpentry, and 6 weeks for construction. The Quonset Hut provides shelter at 1/10 the cost and 1/20th the time. By mid-1944, the United States military had deployed over 160,000 units to every combat theater, providing housing for nearly 6 million personnel constructed in less than 2 years. Guadalcanal, August. The initial combat deployment of Quonset huts occurred on a beach where temperatures consistently hovered around 95 degrees Fahrenheit with 90% humidity. Japanese bombers made daily incursions, cratering anything resembling American infrastructure. Marine engineers unloaded the flat-packed steel panels under sporadic artillery fire and began assembling them within a coconut grove still bearing the scorch marks from the previous week's bombardment. Within 12 hours, Henderson Field possessed 10 new structures, providing housing for the maintenance crews servicing the beleaguered F-4F Wildcats operating from the airstrip. The true test came 3 days later, during a Japanese bombing run that resulted in a near miss. A 500-pound bomb detonated 40 yards from a hut filled with aviation mechanics. The shockwave flattened surrounding palm trees and shredded canvas tents as if they were tissue paper, yet the Quonset structure flexed. Dirt and shrapnel rattled against the corrugated steel. When the smoke cleared, the structure remained standing, with every man inside shaken but unharmed. The jungle environment proved as formidable as enemy action. Within 2 weeks, red rust streaks appeared on any ungalvanized fasteners. The salty air corroded standard hardware with alarming speed. Fungus proliferated on any surface retaining moisture, transforming the interior surfaces into abstract displays of black and green mold. The ventilation louvers, which had seemed adequate during testing in Rhode Island, barely managed to circulate the stifling air. Marines began propping doors open 24 hours a day and cutting additional ventilation openings with tin snips, deviating from structural specifications but rendering the huts habitable. These field modifications were meticulously documented and forwarded to Quonset Point, where engineers integrated them into subsequent production runs, incorporating enhanced ventilation, larger louvers, and galvanizing every single fastener, irrespective of its location. Iwa, February 1945. The volcanic island presented a different kind of hardship. Black sand infiltrated every crevice. There was no topsoil for anchoring stakes, and the constant threat of artillery from Mount Suribachi loomed. Seabees arrived on D-Day +2 and commenced the assembly of Quonset huts under active fire, literally bolting panels together while mortar rounds impacted 200 yards away. The volcanic sand rendered traditional stake anchoring impractical. Consequently, crews improvised by filling empty oil drums with sand and attaching cables from these drums to the hut bases. When a Pacific typhoon struck in March, boasting winds of 110 miles per hour, those improvised anchors held firm while wooden structures across the island disintegrated. The base commander's report to Pearl Harbor was concise. The Quonset hut survived. Everything else was lost. The Arctic environment subjected the design to its opposite extreme. The Aleutian Islands campaign in Alaska saw Quonset huts deployed at Dutch Harbor and Adak, where temperatures plummeted to -40 degrees Fahrenheit and winds frequently exceeded 100 miles per hour. The extreme cold rendered the steel brittle, and early units experienced panels cracking at the bolt holes. Engineers responded by specifying cold-rolled steel with a different metallurgical composition for Arctic deployments and incorporated rubber gaskets at each joint to maintain flexibility. Heating the huts introduced its own set of challenges. Warm air meeting frozen steel resulted in condensation, which effectively rained inside until crews learned to install insulation blankets and maintain ventilation even in sub-zero temperatures. By the winter of 1943, weatherized Quonset models included internal insulation batting, double wall construction for extreme cold zones, and modified ventilation systems designed to prevent heat loss while managing moisture. North Africa and Italy introduced entirely different obstacles. At Palermo, Sicily, a Quonset hut utilized as an ammunition depot sustained a direct hit from a German 88mm artillery shell. The shell penetrated the steel exterior, detonated within crates of small arms ammunition, and the resulting explosion should have theoretically obliterated the structure. Instead, the arched shape channeled the blast force outward through the walls and roof in a manner that left the structural frame twisted but upright. Explosive ordnance disposal crews examining the wreckage noted that a rectangular building would have collapsed entirely, entombing anyone in the vicinity beneath tons of debris. The arch's inherent strength, a compression ring effect, ensured that even catastrophic damage did not result in complete structural failure. The Pacific typhoon season of 1944 delivered the ultimate stress test. Super Typhoon Cobra struck the Philippines in December with winds measured at 140 miles per hour and a storm surge of 20 feet. At Tacloban, the storm annihilated 80% of all structures on the base. Wooden buildings disintegrated into splinters. Concrete block structures collapsed when the wind undermined their foundations. However, of the 43 Quonset huts present on the base, 39 survived intact and 4 sustained repairable damage, exhibiting bent panels and torn seams, but no catastrophic failures. Engineers analyzing the survivors concluded that proper anchoring was the single most critical factor. Huts with adequate ground attachment withstood the storm, while those with improvised or insufficient anchoring were swept away like tumbleweeds. By the conclusion of the war, performance data from 50 combat zones contributed to continuous design improvements. The 1945 production models bore little resemblance to the 1942 prototypes, featuring enhanced ventilation, stronger fasteners, improved insulation options, and field-tested modifications that elevated a good design into an exceptional one. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Suddenly, the United States military possessed approximately 170,000 Quonset huts scattered across 6 continents, with absolutely no clear plan for their disposition. The original intention assumed these were temporary wartime expedients slated for demolition or abandonment once permanent facilities could be constructed. However, something unforeseen occurred. Nobody wished to part with them. At hundreds of military bases designated for closure or downsizing, commanders viewed their Quonset huts not as obsolete wartime relics, but as perfectly functional buildings requiring no maintenance costs and amenable to virtually any repurposing. The War Assets Administration, tasked with liquidating surplus military property, found itself confronting an unusual situation. Demand for used Quonset huts exceeded available inventory. Returning veterans encountered a severe housing shortage, leading families to reside in converted chicken coops and share apartments with 3 other families. The construction industry, depleted of materials and labor during 4 years of war, could not build rapidly enough to meet demand. Into this crisis stepped the Quonset hut, now accessible for civilian acquisition at liquidation prices, ranging from $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally, assuming contractors could even be secured. The federal government actively promoted this repurposing through programs that prioritized veterans for Quonset purchases. By late 1946, suburban developments composed entirely of Quonset huts began to emerge around every major city. Roger Young Village in Los Angeles housed 750 families in converted military huts. Vetville developments sprang up near universities, where the GI Bill inundated campuses with students requiring immediate housing. Architectural adaptations quickly became creative. Families added wooden facades to the curved ends, altering the structure's appearance from military surplus to charming cottages. Interior walls divided the open space into bedrooms, living areas, and kitchens. Windows were cut into the steel sides, a departure from every structural principle, but rendering the spaces genuinely livable for family life. Some owners went further, partially burying the entire structure for earth-sheltered insulation or connecting multiple huts end to end to create sprawling compound homes. Housing inspectors and building code officials initially expressed reservations about approving these modifications. However, the dire housing shortage compelled municipalities to reluctantly grant permits. In Portland, Oregon, an entire neighborhood, Fairview Addition, consisted of 350 Quonset homes. Residents cultivated gardens, painted their steel walls in cheerful hues, and constructed conventional-looking porches that masked their utilitarian origins. Churches discovered that Quonset huts addressed a different need, providing worship space for burgeoning suburban populations without the decades-long capital campaigns required for traditional church buildings. First Presbyterian Church of Levittown, Pennsylvania, conducted services in a Quonset hut from 1952 until 1967, when they finally amassed the funds for a conventional sanctuary. Dozens of congregations reached the same conclusion. $2,500 for immediate space was preferable to $150,000 for eventual grandeur. The acoustics were poor and the aesthetics underwhelming, but individuals could gather for worship the following month rather than the following decade. Some of these temporary church huts remained in service for 30 years, outlasting the generations who initially perceived them as stopgap solutions. Education saw similar adoption. Post-war school enrollment surged with the baby boom, presenting school districts with the same impossible equation that had challenged the military in 1942. The immediate need for classrooms versus the years required for conventional school construction. Rural districts, in particular, embraced Quonset classrooms. A single hut provided space for 30 students at 1/10 the cost of traditional construction. By 1950, an estimated 3,000 schools across the United States incorporated at least one Quonset hut classroom. Some students spent their entire elementary education within these steel tunnels, learning multiplication tables and history lessons beneath curved ceilings that had once sheltered B-29 crews in the Pacific. The commercial sector joined the trend. Small businesses, machine shops, auto repair garages, warehouses, and agricultural equipment storage facilities recognized that Quonset huts offered clear-span space devoid of internal support columns, making them ideal for industrial operations. A welder could establish a workshop in a surplus hut for less than 2 months' rent in conventional commercial space. Agricultural use proved particularly widespread. The original Strand Steel Corporation, having contributed to the design of military Quonsets, resumed manufacturing civilian versions specifically marketed to farmers. Thousands of Midwestern farms acquired Quonset storage buildings for grain, equipment, and livestock shelter. Maintenance requirements were minimal: a yearly exterior hose down, occasional bolt checks, and the structure endured indefinitely. This civilian adoption fostered an unintentional architectural legacy. Quonset huts became ingrained in American visual culture as embodiments of practicality over pretension, function over form, and resourceful ingenuity. They appeared in films, television programs, and photographs as shorthand for post-war optimism blended with austerity. Architectural historians initially dismissed them as ephemeral structures, but by the 1990s, preservationists began recognizing surviving Quonset huts as significant examples of adaptive reuse and vernacular architecture. Several attained historic landmark status, preserved as representations of a unique era when military technology successfully transitioned to civilian life. Contemporary disaster zones vividly illustrate why the Quonset Hut's fundamental design principles continue to reappear in 21st century emergency response. When the 2010 Haiti earthquake devastated Port-au-Prince, relief organizations faced the identical challenge confronted by American military planners in 1942. Immediate shelter for hundreds of thousands of displaced individuals, the absence of existing infrastructure, insufficient time for conventional construction, and conditions that rendered inadequate temporary housing unusable within months. The solution that emerged directly mirrored Quonset principles, even when designers were unaware they were channeling 1940s military engineering: arched steel frames, corrugated metal panels, and prefabricated components that shipped flat and assembled quickly. The fundamental formula remains unchanged because the underlying physics and logistics have not changed. The United Nations High Commissioner for Refugees currently employs shelter systems known as RHUs, or refugee housing units, which are essentially Quonset huts enhanced by 80 years of material science advancements. Instead of corrugated steel, they utilize insulated composite panels. Rather than bolted assembly, they employ snap-fit connections. However, the core concept remains identical: a curved profile for structural efficiency and wind resistance, a self-supporting arch eliminating internal framing, and flat-pack shipping enabling massive quantities to reach remote locations, with assembly by unskilled labor using minimal tools. A two-person crew can erect a modern RHU in 4 hours, aligning almost precisely with the 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle East, and Asia. Hurricane-resistant construction has rediscovered arch geometry after decades of building conventional rectangular structures that hurricanes repeatedly destroy. Following Hurricane Katrina's devastation of the Gulf Coast in 2005, engineers studying surviving buildings observed that curved structures consistently outperformed rectangular ones. The Mississippi coast witnessed entire neighborhoods of conventional homes reduced to foundation slabs, while a handful of Quonset-style metal buildings stood intact with only minor damage. This empirical evidence spurred research into what structural engineers term aerodynamic architecture, designing buildings that work in conjunction with wind forces rather than resisting them through sheer strength. The resulting structures bear a striking resemblance to Quonset huts because the fundamental physics remain unchanged. Wind flowing over a curve generates less pressure than wind impacting a flat surface, precisely as it did in 1942. Today, the modern tiny house movement unknowingly reinvents Quonset principles as designers seek maximum interior space with minimal materials and cost. Several companies now manufacture prefabricated cabins with arched roofs, employing the same corrugated metal and self-supporting curve pioneered by Otto Brandenburger. These are marketed to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. The marketing emphasizes sustainability and modern design, rarely mentioning that the fundamental architecture originates from a World War II military shelter. Some high-end architectural firms have elevated the aesthetic, designing luxury versions with floor-to-ceiling glass end walls and premium finishes, commanding $300 per square foot while retaining the signature curved profile. The arch has transitioned from utilitarian necessity to a design statement. Military applications never truly ceased. The United States Armed Forces continue to deploy arch-style shelters in conflict zones. Afghanistan, Iraq, and classified locations all feature modern descendants of the original Quonset. Current military specifications mandate units that can be helicopter-lifted to mountain bases, assembled under combat conditions, and withstand improvised explosive device blast waves. The materials have evolved, incorporating aluminum alloy frames, Kevlar-reinforced panels, and climate control systems. However, if the 1942 Quonset Point engineering team were shown a 2025 military deployable shelter, they would immediately recognize their own design philosophy. Recent innovations include expandable versions that deploy from shipping containers, unfold like origami, and lock into rigid arch structures within an hour. The economic rationale that justified Quonset huts in 1942 remains compelling today. When disaster strikes or rapid deployment is required, conventional construction simply cannot compete on speed or cost. A modern engineered arch shelter provides weather protection for approximately $50 per square foot, including shipping and assembly. Conventional construction in the same locations, assuming contractors are even available, incurs costs of $150 to $300 per square foot and requires months instead of days. For humanitarian organizations operating on donor funding or military logistics managing trillion-dollar budgets, this cost differential is profoundly significant. The fundamental mathematics that drove Quonset development, how to shelter the maximum number of people for the least amount of money in the shortest possible time, has not changed because the economics of scarcity remain constant. Perhaps the ultimate validation comes from space exploration, where NASA and private space companies designing Mars habitats consistently arrive at Quonset-like solutions. Proposed Martian shelters feature arched profiles to withstand the planet's severe dust storms, prefabricated components that ship on spacecraft, and self-supporting structures that do not require extensive foundation work. In Martian regolith, the constraints of interplanetary construction, extreme environments, minimal tools, unskilled assembly, and maximum strength from minimum materials so precisely mirror the challenges of the Pacific Theater in 1942 that engineers independently rediscover the same solutions. When humans eventually construct permanent shelters on another planet, there is a reasonable likelihood that those structures will owe their design lineage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an intractable problem with corrugated steel and brilliant simplicity.